Okay, so I had to use a different start of it. It was being a little glitchy. So hopefully you are seeing this live. Okay, I had to start a new link, so I'm just going to give a few minutes for everyone to get here, and hopefully you are able to see and hear. Okay, so I'm just going to give a few minutes. Just getting this situated. All right, so now I got the chat working. Again, I'm just going to wait a few minutes, so I'm just going to mute my mic for a moment as I just wait and see, and I'm going to go a little bit past 7 just to make sure I get a whole hour in. I'm just going to kind of update the link that I have on YouTube. So all right, here we are. I apologize for that. I had a little bit of glitch. Now, last time the camera was a little bit wonky and it was really out of sync. So if there is a lag, please let me know and I will turn off the camera. But I'm using a different program, so I'm hoping the lag is not present this time. Okay. So what I want to focus on today in this review, and why I wanted to add an extra review session, is I wanted to focus on the reference tables. And quite frankly, tomorrow in one day, I'm not going to have time to go through everything that I want to. So I'm going to kind of go table by table, give you some example questions, talk about what information you can get from the reference table. Because in reality, the reference tables are a key part of understanding what you need to for this exam. So first, table A, which lists STP, standard temperature and pressure. I think this is fairly obvious what it has, included. One thing to realize is that it does work with the combined gas law formula, and we will look at an example with that. Okay, so the combined gas law, it's important for table A. So you could be asked to convert from atmospheres to kilopascals or from kilopascals to atmospheres because you have this conversion factor from the table. So you can see literally that 101.3 kPa equals 1 atmosphere. So you can set it up just as a simple conversion like this. You could also in your head realize, if 1 is 101.3, then 2 is 2 times that. So the answer is 202. So that's fairly simple, but it is a question that still some people get wrong. So you should know about it. Next, 0 Kelvin, you should know absolute zero. That's not on table A, but is related to temperature. It's the temperature at which particles are moving the slowest that they can be, okay? And here's an example where it is a combined gas law formula. How do I know? Well, first, giant red flag, it mentions the word gas. And the next series of red flags would be, look, it talks about pressure, it talks about temperature, it talks about volume. So we will look at this formula later, but just as a quick recap, P1 V1 over T1 equals P2 V2 over T2. Okay, now what you should realize is this gives me 1 pressure, 1 temperature, and 1 volume. So a lot of times students get stuck here and don't realize how you get to the answer because it says right here, calculate the volume of the nitrogen at STP. So that means STP is what I put for the final volume. The final volume is what I'm calculating for the final pressure and for the final temperature. So my pressure up here was in atmospheres. So you pick the atmosphere standard pressure. The temperature has to be in Kelvin. So you use the Kelvin STP. So those values would go here in the formula, allowing me to solve for this. Okay, so that is just important to realize that you use STP values often in a combined gas law question. Table B, fairly straightforward, lists the physical constants for water only. If you are asked to find heat of fusion, heat of vaporization, or specific heat capacity for something else aside from water, you have to be given that information. So you either have to be able to calculate it because you're given everything else in the formula, or you simply have to be given it in a data table or in the reading of the question. So heat of fusion is the heat needed to change a substance, to change 1 gram from solid to liquid. Heat of vaporization, changing 1 gram from liquid to gas. And the specific heat capacity is raise the temperature. So specific heat involves a temperature change, 1 degree Celsius. Now, the interesting thing is that if you have a high specific heat, then it's hard to warm it up. But the bonus is it stays warm longer. Now, why does that matter? Because literally water. So water does have a relatively high specific heat capacity. And so it takes a little while for it to heat up, as anyone who has been boiling water waiting for noodles knows. Okay? But it also takes a while to cool down. And why is that important? Literally life on the planet. Okay, so water retains its heat well also because of the specific heat capacity. So some things that you should know to be able to use table B as well. Another word for fusion is melting. To do a formula calculation like this, how much heat energy must be absorbed to completely melt 35.0 grams of water solid, which is ice, at 0 degrees Celsius? Well, I would need the Q equals MHF formula. Why? Because it says melt. Melt is fusion. And then I just plug the numbers in and get the answer. Now, if the question does not say round to a certain number of significant figures, you can just literally write what's on the calculator. You do not have to round. Okay. Table C, this is used probably the least aside from identifying key prefixes like kilo and milli. Sometimes something small like nano, but most often that's not used just as often as other ones. Now you can build the staircase, which allows you to see the conversions. So if you're going from kilo to base unit, for example, I moved 3 steps this way, so the decimal goes 3 in that same direction. But you don't have to do this in order to understand what to do. So my recommendation is just literally know this conversion factor. Know this, that there are 1,000 milliliters in 1 liter, and also that there are 1,000 grams in 1 kilogram. And those are really the 2 conversion factors that you need in order to do any conversion they would ask you to do on the exam. I have not seen other ones, so that is a safe bet. Know those 2. Okay, table D. Table D literally just lists units. So if it says a question like, what unit is used? Please, why are you not looking at table D? That is where you should be, okay? So what units are used to measure heat? So you go, and this is one that has a whole list of things that it is used for, and that's going to be joules, okay? Here is an important note. Temperature is not, like capital N-O-T, not a form of energy. Common question. Temperature is a measure of average kinetic energy. Heat is moving energy. So heat is thermal energy, and it flows from high temperature to low temperature. Some requirements, just to cover that real quickly. Objects must be touching for heat to flow. Okay, so if this block is at 50 degrees Celsius and this block is at 70 degrees Celsius and they are touching at different temperatures, heat will flow. What direction will heat flow? From the warmer object to the colder object. So when they ask direction, they're not asking literally north-south. It means from what to what. So from the warmer object to the colder object. So it would go from the 70 degree block to the 50 degree block. Something else you should also realize is that room temperature is somewhere between 20 and 25 degrees Celsius. So a lot of times for these heat flow questions, you have to incorporate air into it because those objects are touching air as well. And so we compare 70 and 20. 70 is greater, right? So heat will flow from the block to the air. And then we compare 50 and 20, and 50 is also greater than 20. So heat will flow from the block to the air. If we had an ice cube at 0 degrees Celsius, right, then heat would flow from the air to the ice cube. All right, so just make sure you do understand heat flow. What is the SI unit for temperature? That's Kelvin. That's the one we want to use, especially in the combined gas law formula. You have to. And remember, in order to do the conversions, there is a formula on table T. All right, table E is next. So table E lists a whole bunch of polyatomic ions. So there's a bunch of things about polyatomic ions that you should know, okay? So first of all, the atoms inside the polyatomic ion are covalently bonded to each other. And it should make sense because for the most part, if you look through, you're going to see all non-metals. And non-metal bonded to non-metal is a covalent bond. So polyatomic ions are held together with covalent bonds. All right. But they also have a charge, and that charge is indicated on table E up here. All right, so basically, again, multiple atoms bonded. And here is another little fun fact that you should know. Every single compound, remember, a compound is going to have no overall charge because the charges balance out. All compounds that contain polyatomic ions, one or more, have both ionic and covalent bonds. So look at an example, I'll show you what I mean. Okay. So what is the name of the polyatomic ion in here? Okay, now it doesn't look like there's a polyatomic ion, but when you start scanning through the list, here is one that is often forgotten. But if they literally ask a question that what is the name of the polyatomic ion in there, then you just have to go and look for it. Okay, and there it is, correct. Now, which polyatomic ion contains the largest number of oxygen atoms? Now, this is not usually a willy-nilly, they just give you one thing, but I can just scroll through and I see this one literally has 7. I see ones with 4, a bunch with 4, but that one is the only one with 7. What is the charge of a carbonate ion? So that's literally you find carbonate, right? And you look at its charge, so -2. And you could write 2 negative. Literally nobody cares, honestly. All right, what is the IUPAC formula of ammonium nitrate? Now, here's the beauty. It does not end in IDE. So that means I have to use table E. So there's like a red flag. Ammonium, you look it up, bam, formula. Nitrate, look it up, find it, formula. Now let's look at the charges. Nitrate is +1. Ammonium is +1 and nitrate is -1. So +1 and -1 already balance each other out and give me 0, which I need. So it's just simply this. I just switch the symbols together and I get the formula. Okay. What is the IUPAC formula of barium sulfate? Well, barium for sure is not here. So I'd have to go to the periodic table. And then I would have to look up its charge as well. So turn off the pen and let's go here let's look at the reference table really quickly. All right, so when I go to the periodic table, all right, here is barium and its charge right here is +2. Okay, so I definitely need that here. All right, so I need the charge of barium, which I said was +2, and then sulfate. Now it doesn't end in IDE, that means it came from this table. Okay, and you find it right here, and look, that charge is -2. Oh, beautiful, perfect. A +2 and a -2 give me 0 when I add them together, so I just squish the symbols together, voila, formula. What is the IUPAC name of this? Well, I need the name of this. You should know that one, sodium. And then this, okay, when it has more than 2 elements, you know I'm finding something on table E. So then I go and I look here and I keep looking, and sometimes you miss it at first and then you find it. Now, why was this the formula? Because that was +1 and that was -1. So the name is sodium hydroxide. What is the IUPAC name of this? Now, this has a subscript. So why does it have a subscript in the formula? Well, I needed it to balance the charges. Why? All right, let's go back and look at the periodic table for a moment and look at magnesium. So here's magnesium with a charge of +2. All right, so this has a charge of +2. And cyanide, right, has a charge of -1. So a +2 and a -1, they do not give me 0. So that means I would need to add another CN with a negative charge. That would give me -2, which would balance out. Okay, so that's just why the formula looks like that. But so the name is simply magnesium cyanide. When you get something from table E to name, that's like literally so easy. They like gift wrap it for you. Okay, on to table F. All right, so table F talks about solubility. It does have this important note here, which says compounds having very low solubility in H2O with this symbol, which is up here. So insoluble means really low solubility. Okay, now why is that important? Because there's this word electrolyte. Right? An electrolyte is something that conducts electricity when it's dissolved in water, right? And the things that are electrolytes are acids, bases, and salts. Now, even the insoluble salts are electrolytes. Why? Because a little bit dissolves, and that little bit that dissolves conducts electricity. Because here's what's key. Conduct electricity from moving electrons or moving charges. Okay? So ions, if they're able to move around, conduct electricity. Electrons that move around, like in a metal that has electrons in a mobile sea of electrons, it can conduct electricity. So in order for something to conduct electricity, its ions have to be moving. Okay? Which is why a salt, like sodium chloride, think about table salt, as it is just a solid, does not conduct electricity. Why? Because its ions can't move. Okay? If I dissolve it in water and now it's aqueous, now its ions can move. It is an electrolyte. It is a conductor. If, on the other hand, I melted it, and so that's a cursive L terribly, but it's there. If I melted it and it's a liquid, guess what? The ions can move. So ionic compounds are going to conduct electricity either dissolved in water or melted. Okay, so that's just a fun little kind of tangent, but super relevant here. All right, so again, using the table, you have to determine if something is soluble or not. Okay? Basically, the key here is pay attention to exceptions. All right? If there are no exceptions, that's easy peasy. So, for the example, this says, which compound is least soluble? So, I know right away I'm looking for something that is insoluble. So, I'm going to point out something about this, potassium sulfate. I see sulfate, right, as a rule, and at first glance you probably don't see potassium. And here's what I'm going to show you. Do you see this? Group 1 ions. Like if I were taking this exam and I wanted to write down something right away so I didn't forget it when I got to this table, I would probably write down that for sure potassium. They don't often ask about rubidium, cesium, and francium, but you have to realize that it just said Li and Na, but there are a lot other elements in group 1. So this group 1 says Li, Na, etc. One of them for sure is K+. So that's potassium. So that means it has no exceptions. It's always soluble. That is a wrong answer. Now let's look. Is there anything else that is in no exceptions? Here's what I'm looking, right? I want to find no exceptions. Look at this, acetate, right here, no exceptions. That's for sure soluble. So now I have 2 options left, either this one or this one. So let's just look at copper chloride. So that falls here for halides. Is one of the exceptions copper? Nope. So that means that stays soluble. So let's see why iron hydroxide would be insoluble. So here's hydroxide. It says exceptions when combined with group 1. Well, we just looked at group 1. That's not iron. It's not this. It's not this. It's not this or this. So yes, in fact, that one is the answer. Okay? So which of these salts is the best electrolyte? So I'm looking for something that is soluble. And here I see it right away. Look at this. That's beautiful. Sodium. Sodium is literally always soluble. It has 0 exceptions. So that is the answer. As soon as I see something like sodium, lithium, ammonium, I am like, this is easy. I can do this. Which of these saturated solutions has the lowest concentration of dissolved ions. So all you have to do is think about, what am I looking for? Well, if I want low concentration of ions, I need insoluble. And why is it worded like that? Because remember, even insoluble dissolves somewhat. Okay, so I should automatically eliminate sodium, right? Off the bat. Okay, everything else is with chloride. So I have to look at chloride. All right, and chloride is soluble, right? So I need to find an exception because I am looking for insoluble. And then right here you see, there's the exception. Ag fits there. All right, and then which ion, when combined with chloride ions, forms a precipitate? So what is a precipitate? It's when you have a solid and a liquid, and then the solid settles out. Okay, sometimes that forms from a saturated solution that comes from a supersaturated one. But also if you like take two liquids and mix them together. And again, this one is looking for, with chloride, which one is the exception. And it's PB in this case. Table G. Okay, Table G has a lot in it, so it talks about solubility. I'm going to show you something to remember about the graph in a moment. This all talks about water as the solvent. Okay. When you have something saturated, it's going to be on the line. So when we look at the graph, I'll show you. Okay. Here is what is important. See this scale? If a solution has less than or more than 100 grams of water, you have to adjust the grams of the solute, okay? Because this graph literally only applies if you have 100 grams of water. If you don't, you have to make adjustments. So if you only have 50, you have half as much water, so half as much solute. If you have 200 grams of water, you have twice as much water, so twice as much solute, okay? In general, solubility for solids increases with temperature. So you can see most of these graphs go up like this, right? And for most gases, it is going to decrease. So solubility will decrease as we increase temperature. All right, so name a compound that shows a decrease in solubility from 0 to 50. So we're only looking here, right? And I want something that shows a decrease in solubility. So look, which lines are going down? It's one of those three answers, okay? A solution contains 35 grams of KNO3 dissolved in 100 grams of water. Beautiful, love it, means I can use the graph at 40 degrees Celsius. So let's just find where we are. 40 degrees Celsius, right? 35 grams, so that's halfway between here. Okay, so 40 degrees Celsius and 35 grams. So we'll say right about here, right? And what line are we looking at? KNO3. So first let's look where we are. Where is this point compared to this line? It is under. So right now it's unsaturated. So the question says, how much more KNO3 would we have to add to make it saturated? Well, it's saturated when it's on the line, right? But it didn't say I changed the temperature. So you go up from 40 until it hits the line. So maybe like, what, 63 or so? I'll say 63 right now. 63 grams is what it could hold, but I only put 35. So how would I find out how much? I'm going to subtract them, right? Now, if this math right here, 29 grams, is done using 64 minus 35. And this just goes to show you have a range of answers. Now, you're not going to be able to put 20 grams as the answer, but you are going to be able to put, if 29 is the accepted answer, you're going to have a little bit of flexibility on either side. All right, a saturated solution, what does that mean? On the line. Of NaNO3 is prepared at 60 degrees Celsius. So I'm going to get where I am right now. 60. NaNO3 saturated, so boom, on the line. Okay. So what can I tell? Well, I could go over and see you know, say I have about 126 grams in there, okay? The solution is cooled to 10 degrees Celsius, okay? And some of the solid precipitates out of the solution. Well, because that makes sense. As it cools, it's not going to hold as much. About how many grams settles out? Well, at 10, it can hold 80, right? So how much precipitates out? 46. Why? 126 is what it was holding at 60 minus 80, what it can still hold at 10. So 46 grams comes out. All right, an unsaturated solution is formed when 80 grams of a salt is dissolved in 100 grams of water. This salt could be, so here at 40 degrees Celsius, 100 grams of water, beautiful, but 80 grams of this, so right here. So this point needs to be unsaturated. That means it has to be under a line. Well, it's literally only under 2 lines. And yeah, one of them is NaNO3. A student prepares the solution by dissolving potassium chloride in 200 grams of water at 60 degrees Celsius. How many grams were dissolved? So saturated on the line. Also, hot mess, right? But this temperature. So let's go 60. And what substance? Potassium chloride. So let's go, here's potassium chloride, right? So 60 right here. That's saturated, right? So like 44, roughly. But this is for 100 grams of water, but I don't have 100, I have 200, right? So this is 90, assuming I used 45 to start with. Again, you have flexibility. So if I used 44, what would I write? 88. So you're going to have some leeway on either side. So if 90 is the accepted answer, in this case, at least, no, not at all. I will do that last one. So if I'll just say this, if 90 is the accepted answer, you're going to have some leeway on either side, either less or greater than. Okay, let me just go back here. Okay. Do you mean, hopefully you mean this one, okay? If it was a different one, let me know, but I'll just look at this one really quickly, all right? So it says, okay, again, an unsaturated solution is formed when 80 grams of a salt is dissolved in 100 grams of water at 40 degrees Celsius. So I have some information, which is I have 40 degrees Celsius and I have 80 grams. So that goes right here. That's where the point is, okay? In order for it to be unsaturated, that point has to sit under the actual line. Okay, so I'll finish this one and then I'll do the one before this one also. Okay, perfect. So, no problem. So, in order for a solution to be unsaturated, this point has to be under the line. And it gets a little bit confusing. So, let's look at this line, for example. When I'm comparing this point to the line, that point is above that line, so it would be supersaturated, okay? So in order for this to be unsaturated, it has to sit underneath a line. So here, if I look at this line, oh yes, that point is under it. And Ki, which like its line would continue like this, we just don't see the whole thing, it would also be under that one. So the only two possibilities would be this one and this one. Now, what you have to be careful of, and why a lot of people kind of make a mistake on this one, is these two lines crisscross. So you just have to be careful which one you're looking at, okay? I hope that cleared that one up. I'm going to go again to the one before this. Okay, here we go. All right, let me just erase this So I can kind of start from scratch here. Okay. Yeah, this one for sure. Now that I'm looking at which question you asked me, it does get a little bit confusing. Okay. So what I like to do is start trying to figure out the question right away. All right. So I'm not even going to try and get an answer yet. I'm going to work through the question step by step. So a saturated solution of NaNO3. So immediately I know I have this substance. Is prepared at 60 degrees Celsius. Immediately I know I'm using this temperature. Okay. Also, it said saturated. So what does that mean? So at 60 degrees, I go up until I get to NaNO3's line. And right now, my solution is here. It is on that line, because saturated means on the line. Okay. So that means that's the solution I have right now. Saturated, there's the dot representing my solution. Okay. Now I'll continue reading. If you try and do the whole thing at once, it really does get even harder. So break it apart. Now it says, as the solution is cooled to 10 degrees Celsius. So I'm going like this. So what does that mean? That means literally I'm going to be following the path of this line, that solubility curve, until I get here, which is where 10 is. Okay? And then it says, as this cooling happens, some of this NaNO3 is going to like precipitate out. So it's going to come out as a solid and not be dissolved in the liquid. The resulting solution is saturated, which means it's still on the line. So literally I stayed on the line the whole time and I ended at 10 degrees Celsius on the line. Okay. Now it says about how many grams of NaNO3 settles out of the solution. So what I need to know is how much could the solution hold at first and how much could it hold at the end. Okay. So at first, if you look and you go across here, okay, it's like 125, 126, okay. I'll use 125. That's what I used the first time, I think, when I was looking at it. So 125, that's what it holds at 60. Okay. Then I'm cooling it, some's falling out. I'm cooling it, some's falling out. Falling out meaning it's precipitating. It's like settling at the bottom. So I see liquid, but then I see some solid stuff hanging out at the bottom. And I keep cooling it, and I keep cooling it. Stuff is falling out of solution until I get to 10 degrees Celsius. And now it can only hold 80 grams at that temperature. But I didn't start with 80, right? I started with 125. So if I started with 125, but the solution can only hold 80 right now, and I subtract those numbers, I'm going to get 45 or 46, a number very close to that, as how much precipitates out. So they didn't ask how much it could hold now. What they asked is what came out. And so that was, you had to do a subtraction in order to get there. Okay. I hope that helped and made more sense. That is definitely a tougher kind of question for that one. Okay. All right. So we finished this one. All right. Which compound is least soluble at 100 degrees Celsius? So what you're going to do is find that temperature. What does least soluble mean? It's going to be the lowest line. So that's the one I see right here. Okay. Trick. They love this question. Which salt is least soluble? So the answer, surprise, surprise, is not SO2. Why? Because salt means ionic, which means it's a metal and a non-metal. Covalent, right, would be two nonmetals. Okay, good. I'm glad it helped. So when it says which salt is least soluble at 100 degrees Celsius, I don't want to just look at the first thing, although that might be the answer. I need to just double check and make sure, is it a salt? So I'm going to go from 0 again, right? And what's the first one I hit? SO2. Well, nope, two nonmetals, not a salt. Keep going up. Okay, that's the next lowest. Great. NH3, also two nonmetals, because remember, hydrogen is a nonmetal. All right, so keep going up, keep going up, keep going up. And then I hit this one, which is NaCl. And there we go. Metal, non-metal. That's where I get to that answer. Okay. And which compound is most soluble at 30 degrees Celsius? So what I do, instead of looking from the bottom, I'm going to look all the way at the top, and it's Ki, literally off the chart. Okay. All right, table H. Table H, not a ton of questions on table H, but they're easy questions, so hopefully you know to look there. All right, so a couple of important things. As temperature increases, vapor pressure increases. If something has a low vapor pressure, okay, it's going to have strong forces and a high boiling point. Okay. Also, this dotted line, I'll look at it when we look at the graph. So here we go. So here, it's literally dotted and labeled this. You should know that that represents standard pressure. But what they don't tell you is that that dotted line then represents normal boiling point. So you find the normal boiling point of propanone by where it crosses that dotted line. The normal... Ooh, I'm sorry. Okay, well, I'm going to turn off the camera for a little bit and see if that helps, okay? All right, so let me know if that helps. Okay. So I just turned off the camera, so let me know again if it's better now without it. Okay. So again, this is standard pressure. So that line represents normal boiling point. And wherever the line crosses the standard pressure line is normal boiling point. So each of these substances has a different normal boiling point. Okay, perfect. I'll just leave the camera off as long as you can hear me and see the screen. That's better. All right, as the temperature of a liquid increases, the vapor pressure does what? So look, as the temperature increases, what's happening to vapor pressure? It increases, okay? As the pressure on the surface of a liquid decreases, the temperature at which the liquid will boil what? So it's saying as the pressure, so I'm going down this way, right? So the pressure goes down. What happens to the temperature at which it boils? It also goes down. Why? Because look at this. At 200, a pressure of 200, propanone boils here. But then if we go down to 50, right, propanone boils here. So that decreases. At standard pressure, which substance has the highest intermolecular forces? Highest intermolecular forces means highest boiling point, because if it has strong intermolecular forces, it is going to hold those particles in tightly, okay? And it's going to make it harder for those molecules or particles to escape and become a gas. So, ethanoic acid, because it has the highest boiling point. What is the normal boiling point of ethanol? That should be easy. We talked about it. You're going to go and find where ethanol crosses that dotted line. Go down and read the temperature. I can tell you probably the most common mistake that students make here is that they don't notice that the scale is different. Okay, so you can see that here we're counting by fives, right? But here we're counting by tens, okay? So that's something that students often make mistakes on. So just be careful of that, okay? Which substance has the lowest vapor pressure at 75 degrees Celsius? Literally, they don't even have to basically ask what temperature, because I'm just going to go up from 75. And the lowest vapor pressure, the first one that I hit, okay? All right, table I on heats of reaction, okay? Something to notice at the bottom, it says a minus sign indicates an exothermic reaction, okay? So remember that delta H, or heat of reaction, is something that can be determined from a potential energy diagram. if you know the energy of the products or can read it from the diagram, and you know the energy of the reactants, and you subtract them in that order, because you will get a negative answer for exothermic and a positive answer for endothermic. And remember that positive non-spontaneous reactions have positive delta H's. So that means basically the universe favors less energy. So if a reaction is exothermic, meaning the products have less energy, the universe is like, that is the way to go. Okay? So this says draw a potential energy diagram for the formation of ammonia gas. So you would most likely have something like this set up on the answer sheet, like in your answer booklet, and then to finish it. Or you would be picking it out in a multiple choice question. So I'm going to look for ammonia gas. If you don't remember ammonia, so again, what I want to encourage is that if you don't know something, I don't know, the reference table might be able to help you a little bit. So if I'm like, I don't even know ammonia, like I blanked, I'm stressed, okay? You might be stressed taking the exam. What you should look here, look, see this, aqueous ammonia? There's the formula, okay? So then you go, oh, okay, well, that's nice. So now I want to form it, which means it needs to be a product, right? So I'm just going to start scanning the product, and I'm going to look for, right, the formation of NH3. And there it is. It has a negative delta H value. So its potential energy diagram should look like this, right? Reactants up to activated complex, and the product should be lower, okay? According to table I, now if it literally says according to table I and you don't turn to table I, come on now, all right? But which salt releases energy as it dissolves? Well, releasing energy means what? Exothermic. So I'm just going to scan through them. I'm going to look for, and also notice down here, do you see how they all have, these first set here, see how they have H2O over the arrow? That means I'm putting it in water and dissolving it. How do I know? They all end with aqueous, right? So now I'm just going to look here and see, well, my two options for exothermic are this one and this one. Which one is a choice? That one. About in how many kilojoules of heat are released when 1 mole of aluminum oxide is formed from its elements. So if it's being formed, it's a product. So I'm scanning. Here we go. Also, they like this particular substance a lot. It's asked a lot if they're using a question like this. So how many kilojoules of heat are released when 1 mole of aluminum oxide is formed? Well, here is it's how much heat is being released. But look at this. See that subscript of 2? I mean, the coefficient of 2 right here, the coefficient of 2. So it's negative 3351 kilojoules for 2 moles of aluminum oxide. But I have 1 mole. So what do? I mean, that should be easy. You're going to just divide it by 2. Okay? You have half as much. How much heat is absorbed when 4 moles of nitrogen, that should say of nitrogen monoxide are formed from their elements? So nitrogen monoxide is what? Nitrogen monoxide, 1 oxygen. So again, I'm looking for, there we go. There it is. And see how it has this number? Look at the coefficient. It's a 2. So it's positive 182.6 to make 2 moles, but I made 4, so I'm going to multiply it by 2, right? And again, if the question doesn't say anything about rounding, I don't have to round. All right, table J. Okay, so I'm going to just tell you a couple of tips. This has to do with redox a lot, but some table J tips, first of all, when you're doing redox situations where you have electrochemical cells. So this is a voltaic cell, right? How would I know? It's got a salt bridge. It's got an electrode connected by a wire to a second electrode. It has an electrolyte, right? That's the liquid that allows the ions to move. Why? Because I need those for moving. For, electricity, I need the ions to be mobile, okay? Now I'm going to show a zoomed in piece. So let's pretend this is the electrode, right? Sitting in the electrolyte, okay? Now, let's pretend this is Mg. Okay, so what that means is if Mg is the electrode, inside the solution as an ion will also be magnesium, but as an ion, and it can move around. It can go back and forth, okay? In fact, it'll do that through the salt bridge, right? So the purpose of the salt bridge is to allow those ions to move back and forth so the cell stays neutral. Why? If it doesn't, it gets polarized. What does that mean? You touch one end of the battery, you get a shock. That's terrible. That's awful. Don't want that to happen. So we want the ions to go back and forth. Now, why am I bothering to show you this? Okay, because this, so again, we're assuming this is a very zoomed in section of this electrode. These represent the individual magnesium atoms. So the atoms are stuck on the actual metal piece, okay? The ions can move around, all right? So let's assume that's on this side. That's our magnesium. And let's assume on this side, we have some barium, okay? So on this side, right, here is my zoomed in piece. It's suspended in the electrolyte. And I have atoms. Excuse my terrible drawing here. This is barium. But again, the barium atoms are stuck on the electrode, on the metal piece, but the ions are free. So when I taught this to my students, I said the ions are like free to move about the cabin, and that's the desired spot. The atoms that are on the electrode are like stuck in place, seat-belted, but not just seat-belted. Like imagine you're on a roller coaster and they like, you know, click, 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 really stuck down, it's pressing into you. So these atoms on the electrodes are stuck on here. These ions are like mobile, they're free to move around. So that's the desired location to be. So why am I even telling you this? Because the more active metal, okay, wants to be here. It wants to be as an ion. It does not want to be stuck on the electrode. That is boring. It does not get to do any fun stuff. It's stuck. Okay. So when I am comparing these two metals, and if I want to find out which one is the anode, which one is the cathode, that kind of helps. That little bit of basic understanding can help. Okay. So let's find them on here. So here's magnesium, and here is barium. So first rule that I tell my students, which is true 100%, always true, is that the higher metal is negative. So the most active metal has a minus sign, okay? So barium has a minus sign, no matter what. It doesn't even matter what kind of cell it is. Now, since this is a voltaic cell and it's spontaneous and it changes chemical energy into electrical energy, then the higher metal will be the anode, okay? So that means barium is the anode. Now, if it is an electrolytic cell, it needs a battery in it, and what will happen is that battery is like, magnesium, I know you want it to be the cathode, that's the way it's supposed to be, but yeah, I'm going to force you, like, it's like, you know, when your parent pinches you when you're little to make you do what they want them to do. They want you to do something. So this is the cathode. In an electrolytic cell, the battery is like, no, we're going to swap places. So these two would switch. But that's not what we're looking at here, so let's stay on this one. So what does that mean? Okay, so that means barium, right, wants to be like this, loosey-goosey as an ion, free to move about the cabin. Okay. So more this will happen. The atoms will become ions and lose electrons in the process. And over here for magnesium will be forced to gain 2 electrons and become an atom and be stuck on the boring location of the electrode. Okay. And then something else to remember is we have a fat cat, which means the cathode gets bigger. And we said that magnesium gets bigger, so that makes sense. So this piece of magnesium gets bigger over time. And so that means the number of magnesium atoms will increase and ions will decrease. Okay. If you can kind of figure that out, it really helps with most of the questions. Okay. So, all right, let's continue here. So this kind of lists some of that information, but in words. You can always read it later. I just wanted to give you an example. All right, so it says, which metal reacts spontaneously with a solution containing zinc ions? Okay, so remember what I said before, so think. Okay, so I have ones that are atoms, right? And then I have ones that are ions. And it says it reacts spontaneously with a solution containing zinc ions. So zinc is an ion. If it's spontaneous, it takes zinc's places. Like you do not get to be, free to move about the cabin. It's my turn. But the easiest way actually to answer this question is a really simple, like Sesame Street way. I'll show you. So zinc is right here. Let's find the metals they're asking me about. Magnesium, nickel. Where's nickel? Copper, and silver. So what do you notice? Well, I like to sing the like one of these things is not like the others. So clearly magnesium is above. It's stronger. It is going to say, no, zinc, you don't get to move about the cabin either. Okay. According to reference table J, which of these metals will react most readily with this 1 molar hydrochloric acid to produce this? So again, here's H2. This is probably the easiest way to answer the questions, and I believe in working smarter, not harder. So why make it more difficult? So calcium, where is it? Bam. Potassium, where is it? Bam. Magnesium, where is it? Bam. And zinc. Okay. So I can't do one of these things is not like the others, right? They're all above. So let me go back to the question. It says react most readily. Aha. The most active is at the top, right? Okay. Which of the following pairs represents a spontaneous reaction? Okay, so let's look. We have Ni, right, with Zn. So there's one, right? Then we have, and so I'm going to put this because it has the charge, right? Okay, then we have, so let's just switch the color, Ag with a charge and Cu. All right, and then let's just switch the color one more time. And then we have Al and Mg with a charge. So I can notice a pattern, right? Look, here I have the positive above, here I have the positive above, and here the positive is below. So it's obviously going to be the answer. Again, smarter, not harder. A voltaic cell contains electrodes of magnesium and aluminum, which will be the cathode. So again, magnesium and aluminum, well, literally they're both right here. The higher one will always be negative. It says it's voltaic. The higher one is the anode, so it would be aluminum. An electrolytic cell, electrolytic, contains silver and copper. So again, right here, what's the rule? Well, the high one is negative, right? Unfortunately, because of that battery, that high one wanted to be the anode, but it is going to be the cathode. Okay? And then because of the phrase fat cat, I know that the cathode will get bigger, so which metal decreases in size? Silver, because that's the other one. All right, table K. Table K is relatively simple and straightforward. It is acids, okay? If something is an Arrhenius acid, it is also a Bronsted-Lowry acid, okay? That is 100% sure. Most of the time, you can look for H's at the beginning. Okay, so just to answer your question, was a cathode and an anode? So a cathode is basically, and an anode, in most cases, is going to just be a piece of metal or like a sample of an element. And it is going to have electrons that move. So let's just say this one is the anode and this one is the cathode. Electrons are going to move through the wire from the anode to the cathode always. Okay, so most of the time it's a piece of a metal. But in an electrolytic cell, it could be like a sample of hydrogen gas and a sample of oxygen gas, okay? Or, you know, other elements that make up a simple binary compound. But in most cases, it literally is a piece of metal, an electrode, and the anode. The electrons will always move from anode to cathode through the wire. And the anode will be the high metal in a voltaic cell. And then it swaps places in an electrolytic cell. Okay, I hope that helps a little bit. Okay, table K, pretty simple, so pretty straightforward. Something that you, okay, so a salt bridge. So here I have my partial sketch here. So let's put this into like a beaker and add electrolyte. Electrolyte is a liquid that conducts electricity because it has like an, I'm sorry. All right. Hopefully it'll, let me turn it off and back on for a second. So give me a moment. Okay. Hopefully that helps. Okay. So electrolyte is a solution that conducts electricity. And you're going to have a salt bridge in a voltaic cell. So it's something that connects the electrolyte on both sides, okay? And then ions, so things that have positive charges and negative charges, can move back and forth across the salt bridge. And the purpose is to keep the cell neutral. Okay, so the salt bridge allows ions to move back and forth, and that helps to keep the cell neutral. Okay, so I hope those help. And again, just one last thing here, organic acids that are going to end with this are still acids. That's about the only way that they could really kind of trick you with an acid question. So it says, which substance listed as the strongest acid? You're going to kind of just look for something close to the top of the table. They ask this question less frequently, but you should just be aware that the stronger ones are typically at the top and the weaker ones at the bottom. Which compound is an Arrhenius acid? Well, literally it just means which one is an acid, so you're going to look on table K. Okay? And that's a super straightforward question. What is the definition of an Arrhenius acid? So you should know that it is a substance that produces hydrogen ions as the only positive ions in solution. It could also refer to them as H3O plus ions or hydronium ions, because hydrogen ions are tiny and little and they do not like to be by themselves, so they usually stick onto a water molecule and make H3O plus. And what is the definition of a Bronsted-Lowry acid, which is typically called an alternate theory in the exam? Like, they never name Bronsted-Lowry. They will call it an alternate theory or one theory or another theory. If they mean Arrhenius, they literally will say Arrhenius. Okay? So the definition for this is that it is a proton donor or a hydrogen H plus donor. Now, those are literally the same thing. Why? Because hydrogen contains one proton in its nucleus and one electron in its orbital. So when it loses an electron, the only thing it has left is a proton. So these two things are the same. They could just use the language interchangeably, okay? All right, table L is bases. It's a much shorter table. Something you should just be aware of is, for the most part, they are OH, but you should recognize that organic compounds that end in OH are alcohols, okay? So what you should notice is that it's OH with a metal, OH with a metal, OH with a metal. So they could ask you about another metal with OH, and it might not be on table L. Okay, so just be aware of that. So, which substance is the weakest base? Again, at the bottom of the table, ammonia. Which compound is an Arrhenius base? So again, you're just looking through the list. Now here's where you might get tricked, right? Right here. This is what I was talking about. This, though, is an alcohol. Okay? This is right here, okay? All right, what is the definition of an Arrhenius base? So Arrhenius bases are substances that produce OH negative ions as the only negative ions in solution. And the definition of a Bronsted-Lowry acid, oops, this should be base. See, I was trying to get this all ready for today, and clearly you made some typos. The definition of a Bronsted-Lowry base is a proton or hydrogen plus H plus acceptor, so the opposite of an acid. Okay. Write the neutralization reaction for potassium hydroxide and hydrochloric acid. Now, normally what you are asked is, this question is fairly common, is that you will be given potassium hydroxide and hydrochloric acid like this, and then you will see this in your answer booklet, 2 blanks. So what you have to remember is that neutralization means an acid and a base combine to form water. Why? This OH combines with the H and makes water. So water is H2O, but you can write it as its literal combo, HOH, and that's okay. All right, either one is fine. And then what happens is what's ever left combines together. Now, if there is no subscripts for these, it's easy because that means this is a +1 and this is a -1. So the formula is just KCl. Okay, now if there were subscripts, I'd have to do a little bit differently. I'll show you that in a second. So that's this one. But what if it is, why do we, all right, so when we go through this one, we'll see if this helps a little bit. Okay, so calcium hydroxide, I'll show you that too, okay, with this one. So calcium hydroxide, which I have the formula here, right? Plus nitric acid. So I would have to look it up, okay? If it literally asks me all these questions, it doesn't typically ask me all of this, but let's just assume it is. And nitric acid is HNO3, okay? So HNO3. All right, but normally what will happen is you'll have this at first, and then 2 blanks, okay? So if it's a neutralization reaction, you know that you get water and a salt. Acid plus base yields water and a salt, okay? So water is, the formula for water is H2O, right? But it forms when you take the H from an acid and the OH from a base. So sometimes you will see water written as HOH, or just even like this, HOH. And if you write it like that, that is technically okay. And that's just, normally we write it like this, H2O. Okay, and that's just the way we start it. And why do we start with the H? Hopefully this will answer your question. Is that typically in a formula, we always list the positive ion first. So for example, Na is +1, OH is -1. K is +1, OH is -1. Okay, so since the H is the positive one, we list it first. All right, but you could just write H2O. But what you need to understand, I'm just going to switch the pen color here, is that the OH, right, and the H combined, that is what makes the water. So now I need to write the chemical formula for what is left. Okay, so that's this and this. All right, so this should help you with the charge part, because that's what I'm going to show you. You're going to have to look in two places. All right, so let me get my reference table up here. And where I'm going to go for NO3 is all the way to table E. Okay, and do you see NO3 right here? Okay, so NO3 right here, right? Its charge is -1. Perfect. Now I know that one. Let's go and get the other one. Where do I go for this one? To the periodic table. Okay, so here is calcium, and then you see up here its charge is +2. So now when I go back to this, I know that the charge of calcium was +2 and the charge of nitrate was -1. Now, the charge of the compound has to be 0. But if I have 1 calcium, so I'm just going to write it up here to start. If I have 1 calcium and 1 nitrate, that's 2 positives, right? And that's 1 negative. That will not be 0. Why? Because 2 plus -1 gives me -1. So I need to add another, positive 1. Yes, exactly. Nope, wait, not that way. You're going to want to put the subscript on the other side, and I'll show you. So I need to add a second nitrate. Yes, you do need a subscript of 2, but you just have it in the wrong spot. I'll show you. So this calcium has a total of 2 positives, and if I have 2 nitrates, I have a total of 2 negatives. So 2 positives plus 2 negatives is 0, and that's what I want for a compound. So yes, I do need to use a subscript, not a coefficient. Coefficient would be in front. So what I want to do is write this. So what is my formula? It's, yes, exactly. So it's Ca, right, and NO3. Now, if you say, how do you know that it goes in that order? Well, up here, Ca came first in its compound. Also, remember what I said, that positives get written first. NO3 came second. It also has the negative, okay? And then if I look at my visual, like I encourage my students to just draw something like this. I only have 1 Ca, right? And in a chemical formula, I don't write a 1. I have 2 of these, but NO3 is a group, and it came from table E. And you see how you kind of have like an example right here. OH comes from table E, so I need to put it in parentheses. Why? Because it's stuck as a group. And I put the 2 outside to say I needed 2 of them, okay, in order for this compound to have a total charge of 0. Okay, so I hope that helps. I kind of went a little, all right, makes sense now. So I went a little bit longer than I wanted, but I kind of wanted to finish with this content because this was sort of related together. Tomorrow, what I will do, I will be on again for another review. I will start with table M tomorrow and continue. Okay, so and hopefully then get to some additional review after that. We'll see how far we get. So I'll start with table M and continue from there tomorrow. And hopefully it has been helpful. And if you aren't able to make it, I will still post it online so you can view it later if you are able. Okay? So good luck studying. Hold on, let me just answer your question. So the subscript outside of parentheses affects the element outside. Okay, so this 2 outside, so if we were counting atoms, this I guess this is a good, I'll just cover this quickly. So this 2 outside affects only the elements inside the parentheses. Okay, so if we were counting atoms and we had said, if I have one of these, literally just one, how many calciums do I need? Well, look at calcium does not have a subscript and it's not in parentheses, so I have one calcium. Okay. When I look at nitrogen, nitrogen does not have a subscript, right? So I have one, but it has a 2 outside the parentheses, so nitrogen has 2. 1 times 2. Okay. And then for oxygen, it does have a subscript, 3, and it's also in parentheses. So 3 times 2. So the total amount of oxygen is 6. So in one particle of this, I have 1 atom of calcium, 2 atoms of nitrogen, and 6 atoms of oxygen. Okay? I hope that helps, because this is definitely what you need in order to be able to find like gram formula mass and stuff. Or some questions about how many atoms are in there. So hopefully that helps. Again, I will start tomorrow with Table M. And if you have additional questions, like you have been putting in the chat, if you have them tomorrow, come with those questions, because I'll definitely address any questions that you have in chat. Okay, so you're welcome. I am happy to help. I want nothing better than for all of you to do amazing on this exam. So with any luck, I will see some of you tomorrow. All right, you're welcome, and have a good night.